this class, we are going to start a new chapter, and that is current electricity. So we are going to study in detail about current electricity. But before that, let's understand the basic concepts about electric charges. So in your childhood, you must have tried this particular experiment, very simple experiment. When a ruler is rubbed on head, and when that plastic ruler is brought very close to small pieces of paper, these pieces of paper move upward or will be attracted by the ruler, and hence some of them will get attached to the ruler also. So you will see the pieces of paper dancing out here, isn't it? So what do you understand from this? It means that when a ruler is rubbed with head, that means the hair, okay, then some charge will get generated and will be deposited on the ruler. These charges which are developed on the ruler will then attract the small pieces of paper which are uncharged. So from these illustrations, it's clear that when two things are rubbed together, because of friction, the charges will be developed. Okay? Charges gets developed because of friction. So let's understand the basic concept behind production of electric charges by friction. All right? Now, when the ruler is uncharged, okay, when the ruler is uncharged, will there be electron, proton and neutron? Obviously, all the matters are composed of electrons, protons and neutrons, isn't it? And you must be knowing that in any atom, the number of electrons is always equal to the number of protons. Okay? So let us assume that this particular matter contains 10 electrons, okay, and that's why it must contain 10 proton, okay. So electrons, electrons are negatively charged, that's why it is minus 10, so it has charge minus 10. So protons are positively charged, that's why the total charge of proton is plus 10. So these two are equal and opposite, isn't it? They cancel and the answer will be 0. So what does it mean? It means that an atom is always neutral. Now what happens when two neutral objects are rubbed together? Okay, let's say this is object A, okay, and this is object B. Okay, now these two are rubbed together. Now on rubbing, because of friction, so some heat energy will be developed, isn't it? Now that energy, the heat energy, will now enable the electrons to move from one object to another object. Okay, so all the objects have the tendency to lose electrons, but that tendency is different for different substances. Okay, so let's assume that A has more tendency to lose electrons than B. Then what happens? Because of friction, okay, the electrons from A, okay, some electrons from A will move to B. How many electrons have moved from A to B? There are 3 electrons moved from A to B. Okay, so this is object A. Okay, so what was the initial number of electrons of A? 10. No, protons 10. Now after losing 3 electrons, how many electrons are there in A? It is 7. 10 minus 3, isn't it? And how many protons are present? Protons remains unchanged, isn't it? That's why 10 electrons and protons. Electron has negative charge and protons, they have positive charge. Now let's find the answer. Plus 10 and minus 7. Plus minus you have to subtract. 10 minus 7 is 3 and sign up the bigger number you have to put. So what is the charge of A now? Plus 3. It is plus 3. So what does it mean? Whenever an object loses electron, it will be positively charged. Okay? And this substance B, okay, has got 3 electrons more, no? That's why its charge will be negative. Okay? So after rubbing, okay, as the electrons move from A to B, A will be positively charged and B will be negatively charged, and this will be minus 3. Why minus? Because it has more electrons. And why 3? Because 3 electrons have moved from A to B. Okay? So this is how charges are produced by friction. Okay? So there are 2 types of charges: positive charge and negative charge. When 2 glass balls rubbed with silk are suspended by a thread and suspended close to each other, then we'll find them repelling each other. That means the 2 balls will remain far apart from each other. Similarly, when 2 ebonite rods rubbed with fur are suspended with a thread and placed close to each other, then they are found to remain far apart from each other. That means they will exert repulsive force on each other. But when a glass ball rubbed with silk and an ebonite rod rubbed with fur are suspended close to each other, then they are found to attract each other. Since like charges repel and unlike charges attract, hence these illustrations show that 2 kinds of charges are developed due to friction. So you saw that when there are charged bodies, they either attract or repel. In doing so, they exert some force. Now we are going to find out the value of that force, either force of attraction or force of repulsion. Okay, suppose this is a charged body, okay, having certain amount of charge. Okay, so let's say plus 2 units of charge, and there is another object having charge plus 3 units. So what kind of force exists in between these 2 charged bodies? Yes, the force of repulsion, because they are like charges, similar charges, isn't it? So these 2 will repel each other. So the first body will repel the second body this way, and the second body will exert force on this first body in this direction. Okay, so there will be certain amount of force, and that is what we are going to find out. Right now, suppose we increase the charge on this body. Okay, charge from 2 is increased to, let's say, plus 7. Okay, and on the second body the charge is also increased from 3, it is increased to, let's say, 10. Okay, so what do you expect? There will be force of repulsion, no doubt. Okay, but what do you expect? What will be the force of repulsion here? Will it be more than this or less than this? Yes, the force here will increase. The force here will increase. Now the 2 bodies will exert more repulsive force on each other. Okay, so what does this mean? That it means that the force depends on what? The amount of charge on the 2 bodies. Okay, so force depends on charges, or we can say, so more the charge, more is the force, isn't it? That's why force is directly proportional to the charge on these 2 bodies, that is the product of the 2 charges, Q1 and Q2. Right? Okay then, I'm taking the same charge plus 10 and plus 10 and plus 7, okay? Now, so here they are this much far apart from each other. Now what if I bring the two charges closer to each other? So here is the charge plus 7 and here is the charge plus 10. Now what do you expect? Will the force be more or less than the force here? Since they are closer, they will repel more. So when the two charged bodies are placed closer, the force increases. And what if the charges are separated by more distance, plus 7 and plus 10? In this case, since the charges are far apart, the force will be much less, isn't it? So imagine that you have two magnets out here, okay? North, south, north and south, okay? Now, these two magnets are placed close to each other. So, since the opposite poles are here, what do you expect? What kind of force will be there? Attractive force, isn't it? So, these two will attract each other, okay? Now, what if the magnets are moved little bit away from each other? Now, will the force be more or less? It will be much less, isn't it? Because as the distance increases, the force gets decreased, isn't it? So, similarly, here also, as the distance increases, the force decreases. As the distance decreases, they will repel more and more here, isn't it? So, from here, we find that the force depends also on what? The distance, okay? As the distance decreases, force increases, isn't it? That's just the opposite. As the distance decreases, force increases, and that relation is called inversely proportional, isn't it? Inversely proportional, all right? So there is a certain relation, okay? So it is experimentally found that the power is 2 here, okay? So force of attraction or repulsion between two charges depends on the amount of charge, okay, which the bodies have, and also the distance between the two charges, and that is given by Coulomb's law. The law states that the force of attraction or repulsion between two charges is directly proportional to the product of the two charges and is inversely proportional to the square of the distance between the two charges. So let us assume that this is a point charge Q1 and this is another point charge Q2, and the distance between them, the two charges, distance between two charges, let's say R. So R is the distance. So according to Coulomb's law, the force of attraction or repulsion between the two charges is directly proportional to the product of the charges, isn't it? So what is the product of the charges out there? Q1 into Q2. So this is the first part of Coulomb's law. Second part is that force is inversely proportional to the square of the distance between them, isn't it? So inversely means here inversely proportional to the square of the distance between the two. Okay? So this is how we write Coulomb's law mathematically. Alright? Now let's combine these two to form one formula for the force. If a quantity is directly proportional to another quantity, like A is proportional to B, and the same quantity is proportional to another quantity C, then according to the theory of joint variation, what we do is this. So here we are neither adding nor multiplying. Okay, so here according to that rule, A means A remains as A. We are combining only proportional, and these two, okay, should be multiplied, B into C. So this is the relation for A, which shows that A depends on B also and C also. This is the theory of joint variation. Now let's apply that theory of joint variation to find out a formula for F. So according to joint variation, F and F will give you F. Proportional will remain as proportional, and these two should be multiplied, isn't it? So this into this, okay? So numerator, and this is numerator. Q1 Q2 into 1 is Q1 Q2 upon R square. And in order to replace this by is equal to sign, there must be a constant of proportionality. Okay, so what is K here? K is a constant. K is a constant. Okay, similarly, now F will be some constant into Q1 Q2 by R square. Alright, now the rest I'll do it here. Okay, now in CZS system, the value of K is 1 for air. That means when air is in between Q1 and Q2, the value of K will be like this. When we put K equal to 1, this formula becomes K equals to 1 into Q1 Q2 by R square. So finally F is equal to Q1 Q2 by R square. So this gives us the value of the force of attraction or repulsion between two charges, okay, when placed in air. Now in SI system, the value of K is 1 by 4 pi epsilon naught, where this epsilon naught is the absolute permittivity of vacuum, and the value of all of this is 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, so since we know that the force of attraction and repulsion between two charges is given by the formula K Q1 Q2 by R square, now we simply put the value of K. So it is 1 by 4 pi epsilon naught Q1 Q2 by R square. So this formula gives the value of the force of attraction or repulsion between two charges in SI. Right? Now the same formula will help us to define the unit of charge, the SI unit of charge. You know, the SI unit of charge is Coulomb. Now let's see how this formula will help us to define Coulomb. Okay, now to define Coulomb, what we do is we take this Q1 and Q2 to be equal to 1 unit charge. Okay, and what we do, we separate the two charges by a distance of 1 meter. So unit distance, that is 1 meter. All right, and you know the value of this 1 by 4 pi epsilon naught. This is 1 by 4 pi epsilon naught is 9 into 10 to the power 9 Newton meter square per Coulomb square. No? That's why when we put all these values in this particular equation, the relation becomes F equals to, this is 9 into 10 to the power 9, Q1 into Q2, Q1 into Q2, and R square. So F is, now all of this is 1 into this number is the same, 10 to the power 9. Now force has the unit Newton in SI, no? That's why this much will be the force between two unit charges separated by 1 meter, okay? That's why we define, so this one, the unit value of the charge is said to be 1 Coulomb, okay? Hence we define Coulomb, the amount of charge on a body which when separated by a distance of 1 meter from another similar charge, okay, will experience a repulsive force of 9 into 10 to the power 9 Newton. Electric potential at a point. Now let this be a charged body and let it be positively charged. Why positive? Because we have to think positive and be positive. Now around the charged body at any point you find the electric potential. So let us assume that this is a point A where we need to find out its potential, and of course the meaning of the potential at a point A, okay? Now in order to explain the concept of potential, we have to take a unit positive charge, okay? Unit positive charge, okay? Not very close to A, okay? But at infinity. Although we can't show infinity on the board, so let's, for our convenience, let that point, okay, the point at infinity be at this point, okay? So this is the point at infinity, and at this point we have to assume a unit positive charge. So in order to bring this unit positive charge from infinity to the point A, you know, we have to apply some force, isn't it? And there is a displacement also, isn't it? And whenever there is force and displacement, okay, the product of these two will give you the work. So you see, some work is done in order to bring a unit positive charge which is present at infinity, okay, to the point A. So that work done is known as the potential at A, okay? Hence potential at a point is defined as the work done in bringing a unit positive charge from infinity to that point. So this is the concept of the potential or the electric potential at a point, and you have to know its SI unit also. The SI unit of electric potential at a point is volt, and it is denoted by V, okay? And then the same explanation, okay, will help you to understand the meaning of volt. So what is 1 volt? So the potential at a point, let's say at the point A, is said to be 1 volt, okay, if 1 joule of work, okay, is done in carrying a unit charge. That means 1 Coulomb charge from infinity to that point. So that is the meaning of volt. All right. Now with this, I want to show you another similar topic to you. Now let B be another point, okay, which is closer to the charged body. So what will be the potential at the point B? It's like A, isn't it? Potential at the point B means the total work done in carrying a unit positive charge from infinity to the point B. So in both the cases, you are carrying 1 Coulomb charge, isn't it? But at the point A, this much is the displacement, isn't it? When the charge is brought from infinity to the point B, you see the displacement is more out here, isn't it? Since the displacement is more, okay, the work done will be more, and hence the potential at the point B will be more than the potential at the point A. So, what do you understand from this? As we move closer and closer to a charged body, the potential increases, and as we move away, the potential decreases. Alright? Now, just to understand, okay, let's give the potential some values. Let's say the potential here is 20 volt and the potential here is 18 volt. So you see there is a difference between these two, no? So what is the difference of potential between B and A? This is 20 minus 18, that is 2 volt. And what is that 2 volt equal to? It is 20 minus 18, no? So when you subtract this much from this much, you get this 2 volt, isn't it? That's why we say this is the difference in potential, and it is called the potential difference. So potential difference between 2 points is the work done in carrying a unit positive charge from one point to another, not from infinity to A or infinity to B, from one point to another. That's why the next topic is potential difference. Now, potential difference between 2 points is what? It is the work done in bringing a unit positive charge from one point to another point, and it has the same unit as the potential at a point. So its SI unit is also the same, that is volt. EMF, or the electromotive force of a cell, and by cell we mean an electric cell, not a biological cell. Okay, now before going on to this topic, let's understand about cell, that means electric cell. So what's an electric cell? An electric cell is a device that converts chemical energy into electrical energy. Okay, for instance, the cell which you use in a torch, okay, so that contains chemicals inside it, okay, and that produces the electric current. We have different kinds of cells which you can see out here also. Although they look different, but they all have few things common, okay. They all have two electrodes, one positive and one negative electrode, and they all have one or a mixture of chemicals, and that's called electrolyte or exciting liquids. Okay, so for your convenience, I'm drawing a dry cell. So this is a dry cell. You know, this part is the positive of the cell, and this end acts as the negative electrode of the cell. Okay, so this is how a dry cell looks like. Okay, but in a circuit we represent an electric cell by two parallel and unequal lines, like this, longer line and a shorter line. Okay, the longer line represents the positive electrode of the cell, and the shorter one indicates the negative electrode. All right, so that's all about the electric cell and different types. No, you know, when there are 2 points in an electric field, there will be potential difference between the 2 points, isn't it? Similar kind of potential difference exists in between the two electrodes of the cell also. Okay, so that means this is the positive and this is the negative, isn't it? So this potential difference that exists in between the two electrodes of a cell when the cell is not connected to an external circuit, that means when the cell is open circuited, okay, that potential difference between the two electrodes is known as the EMF or the electromotive force of the cell. Now let's have some examples of the EMF. Okay, different cells have different EMF. For instance, a dry cell has EMF of 1.5 volt, while a Daniell cell has EMF of 1.08 volt. In the diagram, PQ is a resistance that is connected to the two terminals of a dry cell. So as soon as we connect the resistance to the cell, electrons from the negative electrode will flow through the resistance and come back to the positive electrode, and there will be continuous flow of electrons. That means electrons through the resistance will be flowing from, you can see, from Q to P. No? So let's say Q amount of charge flows through the resistance in T seconds. Okay, so in T seconds, how many charges are flowing? Q. So in 1 second, how many charges will flow? So it's Q by T. So what is this? This is the amount of charges that will flow in 1 second. And isn't this the rate of flow of charge? Rate of flow of charge. This rate of flow of charge is known as. So electric current is defined as the rate of flow of electric charge. All right, and the formula for this is, if I be the current, then it is the rate of flow of charge. Isn't this the rate of flow of charge? So it is Q by T. So this is the formula for electric current. Now let's see its direction also. Okay, now in the diagram you can see electrons are flowing from Q to P, isn't it? But by convention, okay, the direction of the positive charge, okay, is taken as the direction of electric current, not the negative charge. Okay, electrons are negatively charged, isn't it? So since negative charge, that means electrons are flowing from Q to P. So we can imagine that positive charges are flowing from P to Q, isn't it? That's why the direction of the current is from P to Q. All right, so you can see from the diagram also, okay, that current always flows from the positive electrode to the negative electrode of a cell through the circuit. And now the SI unit of current is ampere, and let's see its definition also from the same formula, Q by T. If 1 coulomb of charge, okay, flows through a wire in 1 second, okay, the current flowing through the wire is said to be 1 ampere. So that's how we define ampere. It is, let's take few things which flow, okay, like any liquid heat also, it can flow, isn't it? Now, for a liquid to flow, there must be difference of height, isn't it? Because a liquid flows from higher level to a lower level. Similarly, heat also flows from higher value of a physical quantity to a lower value of that physical quantity. What is that? That is temperature, from higher temperature to a lower temperature, isn't it? So heat flows like this, from a point of high temperature to lower temperature, and liquid flows from higher level to a lower level. Now think of electric current. Electric current, like a liquid or heat, electric current also flows, isn't it? And a flowing object, okay, flows from higher value to a lower value, isn't it? Similarly, electric current, suppose if this is a wire, these are the 2 points A and B. If A is at higher value of that physical quantity and B is at lower value, what should this physical quantity be? It is potential. So electric current flows from higher potential to lower potential. All right. Now let's remove heat and let's concentrate on liquid and current only. Now when this much is the inclination and this much is the difference in height, so you can see this is the difference in height, isn't it, of these 2 points. So when this much is the difference in height, liquid will flow with some speed. No? Now what will happen if I increase the difference of level? Initially this much was the difference in level, and now you see this much is the difference in level. You can see the difference has increased, isn't it? Now how will the liquid flow on this surface? It will flow much faster, isn't it? That means the rate of flow of liquid will increase. Okay? So as the difference of height increases, then the rate of flow of the liquid will also increase. Now similar kind of thing happens in case of electric current also. So this is the wire, these two are the 2 points as usual. Let's say A is at a potential 20 volt and B has a potential 18 volt. Okay, so since there is a potential difference, current will flow from higher potential to lower potential. That's why current I flows from A to B. Okay, now what is the difference of potential, or the potential difference here? 20 minus 18 is 2 volt. Now let's see what happens when we increase the potential difference. Okay, now for that what I am doing is I am keeping the point B at the same potential 18 and I am increasing the potential of this to, let's say, 25 volt. So what is the potential difference right now? This means this is 7 volt. So it has increased, no? What has increased? The potential difference has increased. Okay, so as the potential difference increases, the rate of flow should also increase, isn't it? What is actually flowing? The charges are flowing, isn't it? So as we increase the potential difference, the rate of flow of charge will increase. The charges will flow faster and faster, isn't it? And what is that rate of flow of charges called? Current. So what does it mean? As we increase the potential difference, current will also increase, and as we decrease the potential difference, okay, current will also decrease. So that is actually given by the law, which is one of the most important law in this particular chapter, and this is known as Ohm's law. The law states that temperature and other physical conditions remaining the same, the electric current flowing through a conductor is directly proportional to the potential difference between its ends. So it means the same thing, isn't it? That means as we increase the potential difference, current will also increase, and as we decrease the potential difference, current will also decrease. Now let VA be the potential at A and VB be the potential at B. So the potential here is VA and the potential here is VB. Like in the previous case, it was 18, 20 and 18, no? So how we found out the potential difference? By subtracting these two, isn't it? By finding the difference of these two potential. So which is greater? This is greater because current is flowing from A to B. So A is at higher potential. So what is the potential difference here? VA minus VB. And according to Ohm's law, this is directly proportional to the current. And when you subtract the potential of B from potential of A, we get another answer, isn't it? Like the difference of 20 and 18 is 2, no? So 20 minus 18 is 2. This is the potential difference. Similarly, V is the potential difference. VA is not the potential difference. VB is not the potential difference, okay? This is the potential at A, this is the potential at B, and this is the potential difference. So this potential difference is directly proportional to I. And you know, it has to be replaced by is equal to and constant. And what is K here? K is the constant of proportionality, and this constant in this case is R, which is the resistance of the wire. That's why V equals to, this is R and I prefer to write like this, V is equal to IR. This is one of the most important formula of this particular chapter. V is the potential difference, I is the current, and R is the resistance. Now that is the x-axis, and this one is the y-axis. Now if we plot the values of current along y-axis and values of V, the potential difference, along x-axis, then we get a graph like this. That means a straight line passing through the origin, okay? So that oblique straight line means that as the value of the potential difference increases, the value of current will also increase. When the value of the potential difference is 0, the current will also become 0. So this is the characteristic feature of a conductor. Now the limitations of Ohm's law. Ohm's law is applicable only in case of ohmic resistances, okay? It's like the metals, for example, copper, silver, gold, aluminium, okay? These are the ohmic resistances, okay? So these ohmic resistances, okay, follow Ohm's law. But Ohm's law is not obeyed by non-ohmic resistances. like the semiconductors or vacuum tubes. So these are the things which do not follow Ohm's law. Okay, so if that is so, then let's see the graph, okay, V versus I graph for the ohmic resistances, okay, and non-ohmic resistances. For ohmic resistances, V versus I graph will be an oblique straight line passing through the origin. For non-ohmic resistances, the graph will not be a straight line, okay? It will be a curved line somewhat like this. So as the graph goes up, it also means that as the value of potential difference increases, the current will also increase. In this case, the current is not directly proportional to V.